Hello again, mathematicians. I got a question today about logarithms and asymptotes. I want to talk about that a little bit today, but in order to talk about that, I really wanted to do more of a broad scale review of logarithms as a whole and take several steps back in order to really talk about the foundations of what are logarithms. Because oftentimes I find that the biggest confusion points come from not necessarily, I don't know, I don't want to be criticizing a traditional math teacher here, but I don't think that a traditional, typical math teacher necessarily goes into a lot of the background of why for stuff like logarithms. But that stuff I think is really important when you get to the more complex problems. And what I mean by that is it's easy to solve some pretty basic logarithm problems without necessarily understanding where they come from. But I think sometimes understanding kind of the bigger picture is it's really important to know what is a logarithm? What's the foundation of it? So let's start here. PEMDAS. Obviously, we use PEMDAS as our acronym to symbolize order of operations if we are simplifying an expression. Then we would use PEMDAS, right? We simplify everything in the parentheses first, then we do the exponents, we do multiplication, division, and then addition and subtraction last. Obviously, we do not use PEMDAS if we are solving an equation, right? For equations, we go the opposite direction. We use SADMEP, right? And don't believe me? Let's do a really simple equation here. So 5x plus 7 equals, I don't know, 27. Something easy and simple like that. When you're solving this equation as a mathematician who understands algebra, you're not starting by saying, "Oh, no parentheses, no exponent. Okay, let's do multiplication and division now," right? Because you're solving an equation. You're trying to isolate the variable here. You're not simplifying an expression. So instead, we go in the opposite direction. We start with, is there any subtraction or addition? Yeah, there's an addition. Subtract 7 from both sides because we are doing the opposite of addition by subtracting. um, Obviously, the next step you would then divide both sides by 5 because that's the opposite of multiplication, right? So the reason I'm talking about these kind of foundational PEMDAS and SADMAP ideas is because we often teach PEMDAS and SADMAP before ever getting into the realm of quadratics or exponential functions. Obviously, quadratics and exponential functions both have an exponent. The key difference here is where is the variable? Where is x? Is x in the base of this expression or is it the actual exponents, right? So if we have to the power of 2, then we know, okay, cool, we have a quadratic equation, right? Or if it's, x to the power of 3, it's a cubic, or x to the power of 5, right? It's a fifth order polynomial. The not opposite, but the contrasting view of this is if we have a whole number as our base and the exponent is actually the variable, we don't know what the exponent is, then that's a little bit different than a quadratic, right? That's an exponential function. Exponential functions versus polynomial functions, which are, the most basic one is the quadratic. That's the one we come back to the most often, right? Okay. The point here is that if we are dealing with PEMDAS SADMAP, right, we're dealing with the fact that multiplication is the opposite of division, then we can start to define what's the opposite of an exponent, right? Well, if the exponent is a whole value, like x to the power of 2, then the opposite of that is a square root, right? Or let's say we had x to the power of 3, then the opposite of that is a cube root. The index of the root is 3, right? If we had x to the power of 5, right? The opposite of that is the fifth root, right? For exponential functions where we don't know what the x value is, we use a certain rule. And that is where logarithms come into play, right? a logarithm is an opposite of an exponential function. And the main rule that we use to show that logarithmic relationship is if I have a function y equals b to the power of x, then that can be transformed. And I don't think this is super common, but I use this little I just use a little double arrow symbol here for this. That didn't look very much like an arrow. I'm going to make it a little bit more of an arrow there. I use a little double arrow symbol for this just to show that this transformation can go in either direction. We can go from an exponential function to a logarithmic form. We can go from a logarithmic form to an exponential function. And the pattern that we hold here is that the base of the exponential function is also the base of the logarithmic function. So, in the case of y equals b to the power of x, the base is still b, just like it was the base in the exponential function, right? So that makes remembering where these values go a little bit easier, right? Then next comes, okay, what goes here? Well, obviously x is our variable. That's what we're looking for. So that's not going to go here. That wouldn't help us solve the function. Therefore, I know that my pattern has to be log with a base of b to the y equals x, right? So this is our foundational logarithmic rule, transforming an exponential function into a logarithmic function or vice versa, right? So essentially, what this is doing is it's the E step of either PEMDAS or SADMAP, depending on what you're doing. SADMAP more appropriately if you're solving a function. And because we teach this earlier to students, then they are introduced to all of this stuff, right? We don't have a kind of a something that goes with our e here. We don't have something that goes with exponents. For two reasons, I think. One of them is that we teach this stuff to students before we ever introduce all of this more advanced stuff. But the second reason is because what do you use? Do you say L for logarithm? Because that doesn't necessarily cover the scenarios where we have a defined exponent, right? Those are square roots, right? So then do you do SQL? And then, your acronym starts getting messed up, right? But this is where that fits in this scheme. If you go back to remembering this scheme from, like middle school years, really. Um, so here's our foundational principle. I want to talk about this just a little bit longer. Um, in the context of, first of all, what is an exponential function? Just a real quick reminder. And then I'm going to show a few graphs of what this looks like. So, first things first, what is an exponential function? Well, obviously, an exponential function is, and by the way, I'm going to just use this same example, 2 to the power of x, right? So let's do some x values and some y values. Okay, what an exponential function is it is I'm going to take the base and multiply it by itself x many times, right? So when I do this, I'm going to start with a high number for x and go downwards. I'll show you why in just a moment here. So starting with a number like 4. Well, what is 2 to the power of 4? Well, that's 2 times 2 is 4 times 2 is 8 times 2 is 16. What is 2 to the power of 3? Well, 2 times 2 is 4 times 2 is 8, right? The foundational pattern of exponential rules is that if I'm going up in x values by a whole number, then every time this function is being multiplied by the base. In this case, the base is 2, right? So what happens if instead of going up in whole number x values, I go down? Well, the opposite. Instead of being multiplied by 2, if we're going down, we are dividing by the base every time. So we're dividing by 2, right? Well, 8 divided by 2 is 4. 4 divided by 2 is 2. So this means 2 to the power of 1 is 2. Yeah, that makes sense. And then we get to this, I would call it kind of a constant conundrum. Like people who know what something to the power of 0 is, I think oftentimes just know it, right? But people who don't, they're like, well, how could you have something to the power of 0? Well, this is how, right? Is we've followed this pattern where we're dividing by the base. We're dividing by the base. Well, what happens when you divide by the base here? Well, 2 divided by 2 is 1. That is the reason that every single number to the power of 0 is 1. This will happen for all numbers, right? When you divide by the base, you're dividing by that number, which is inherently going to be equal to 1, right? And then the question is, what happens when we get into our negative values? Well, the same pattern starts happening, right? Where you have 1 over 2, because when you do 1 divided by 2, you get 1 half, right? When you do 1 half divided by 2, you get 1 fourth, right? And that is where the foundational exponent rule that, for example, 2 to the power of negative 2 is equal to 1 over 2 to the power of 2, right? Which is equal to 1 fourth. That's what we got up here. Yeah, that agrees, right? That's where that foundational exponent rule comes from, where we say x to the power of negative a is equal to 1 over x to the power of a, right? What this means is that on to eternity, infinity in our mathematical terms, this keeps happening. We divide by 2, divide by 2, divide by 2, divide by 2. So eventually we're going to get down to negative, I don't know, 1 billion, 1 trillion, 1 gazillion, I don't know, right? But we will still never have hit the value of 0, right? We'll never hit that because every single time we're just cutting this in half, right? So by the time we get to negative 1 gajillion as our value here, then all that that means is this is going to be 2 to the power of negative 1 gajillion, blah, 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 right? Which is the same as 1 over a very, 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 very big number, but it's still not 0. It's slightly higher than 0, right? Okay, last little piece that I want to, I don't know, attempt maybe to connect some dots for you here is let's do a bit of graphing. Hope those are all my videos. There's some graphs. Okay, so real quick review of kind of what an opposite function is, right? So, for example, what if I wanted to graph the basic function y equals, I don't know, let's just do 8x, for example, right? Well, we all know that the slope is 8, which means that if I was to do the rise over the run, I could count up 8 values over 1, and that would put me exactly on the next point on this line. I could do the same thing. I could go 8 values down to the left one. Um, but this is my line, right? The question is, what is the opposite of 8 times x, right? Well, the opposite of 8 times x is let's divide both sides by 8, right? That is the same as saying, right? Dividing by 8 is the same as saying times 1 over 8. That's also a foundational rule of mathematics. If I'm dividing a fraction by a fraction, I multiply by the reciprocal of the divisor, or I know a lot of students call that keep change flip, right? So let's do a divide by 8 here and compare this function to a very similar but opposite function of 1 over 8x, right? Well, notice something here. All that has happened is by giving the opposing function for times 8, which is divide by 8, I have now flipped my one or sorry, y equals 8x line. I have reflected it over the y equals x axis. Right? So I have my y equals x axis in red here, right? All that's happened is this line has been reflected over the red line, right? It's a direct reflection. And these two are therefore opposites in the same way that multiplication and division are opposites, right? So, by the way, you may notice if you already have some insights and background into this, I'm trying to not use specific technical math terms right now, right? And we're just saying, okay, this is multiplication; these are opposites. If you don't know what I'm talking about, just ignore that statement. Okay, so we have reflected this over the y equals x line, right? Now I want to do a quick comparison for what we talked about earlier. Let's just use the same quadratic function, y equals x squared, right? Actually, you know what? I'm gonna hold that one off for a little bit. Let's do our exponential function first, and then I'll move this one. I'll make this one be later on. We'll come to that later on. I'm not gonna show it right now. Okay. So let's do an exponential function first. So exponential, as we talked about before, is 2 to the power of a variable like x, right? Well, we know that the appropriate logarithmic function that is opposite of that was signified by our work that we did here, right? So I'm just going to go to a new page and quickly show you what that looks like for y equals 2 to the power of x, right? If we do our logarithmic transformation here, my base is going to be the same, log base 2 y equals x, right? That's what I'm going to graph in Desmos. Now, quick note here, in order to keep this on the same axis, I actually, and this is, by the way, I know, this is going to be confusing, but in order to keep this on the same axis, I still have to have a y equals. So I'm actually going to flip my location of x and y just to be able to show this on the same axis. Sorry if that's confusing. I'm not going to go into more depth on that right now, just because, um, that's a whole nother rabbit hole. Anyway, what we determined then was that what we should use is y equals log base 2, right, to the x. Because again, remember, I'm switching my x and y here, not talking about y. Um, so I actually don't know how to do in Desmos put a little base in, so I'm going to use the foundational logarithm rule that says. By the way, let me just write this just so that we're on the same page. I'm sure that most people who have seen logarithms at all already know this, but another foundational rule for logarithms is that if there is no base to a logarithm specified, then we assume it to be base 10. However, if there is a base specified and we have a calculator that doesn't allow us to use the little subscript symbol here, right? So, like a normal TI-83 won't allow you to do that, then we can always use this logarithmic rule that is equal to log of y over log of b. Now, both of these are now implicitly using the base of 10, even though I'm not writing that in there. But this statement is true. So that's what I've used while I've been graphing this. It's the same thing as saying log base 2x that I've written in here. And as you can tell, what's happened? Well, a logarithm is an opposite, right? Just in the same way that multiplication is an opposite to division, it's an opposite of an exponential function, right? And what has happened? Well, the logarithmic function in purple is a direct reflection over the y equals x axis of the exponential function in green. Now, what we talked about previously on our last page was that this exponential function in green is going to, as we go into negative x values, right? So as we go into negative x values on the left side of my graph here, and we could continue zooming out as far as we want, right? And we can see that these values, like we talked about previously, can get more and more negative, but they're just going to get smaller and smaller and smaller, right? Until, by the way, you're eventually going to get to a point where Desmos says it's at 0, even though it's really not. It's just rounding it, and so it's saying, "Oh, this is at 0 now." But if we were to zoom in closely on that, you would see that it's not actually at 0, right? Um, let's see if we can get close enough on Desmos. I might not even be able to. Oh, there we go, right? So we've zoomed way in, and now we can see, oh, Desmos was just rounding it. It's actually 0.000000 blah 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 79, right? Okay, so let's zoom all the way back out now. Oh, the challenges of just trying to make a point. Um, okay, sweet. So here's our graph. Again, we've noticed that the logarithmic function that I entered is a direct reflection over the y equals x axis from its component exponential function, its partner exponential function, right? Well, The reason I'm bringing this up is just because, once again, this is helpful for us when we're thinking about what sorts of a graph a logarithm will look like, right? We know that because the exponential graph never hits a value of y equals 0, right? We never cross the x axis. We then know that the opposite will be true for the corresponding logarithmic function, right? Instead of never hitting the x axis, it will hit the x axis at the same place, by the way, as the exponential function will hit the y axis, but it will never hit the y axis, right? Which means that the base logarithm function that we have here, I guess I shouldn't call this the base logarithmic function. I would call that just log x, whereas this we have log base 2x. Um, but still, point remains that the base logarithmic function will therefore have a vertical asymptote at 0, right? All of them have to have that unless we do something to that logarithmic function to move it around and change it, right? We'll talk about that in a little bit. I do want to make just one more point about this x squared value, just because even though it's not a logarithm, I think it will help to prove our point. Obviously, the opposite of a x to the power of 2 would be square root. Oops, put too many in there. Right, so square root x, right? Well, notice what happens here. Oh, I uh, made the my quadratic go away. Okay, so notice what happens here also, right? Is my quadratic function is not nice and clean like the exponential function where it was all on one side of my y equals x axis, right? Instead, it crosses the y equals x axis. So, as you might imagine, a direct reflection over that axis for this will also cross that same y equals x axis in red at this point. So, our graph will look like, and now you've already had a preview into what it looks like, a direct reflection over that same axis. There is a difference with the square root function, which is that it stops all of a sudden at 0. It doesn't go into negative values. Now, without going into too much depth as to why that is the case, I'll just pose that as a question for anybody who's watching this video. Why is it the case that that square root function would stop at 0 there? Why is there a dynamic here that would cause that to happen? There is a reason, and it has to do with basically undefined sorts of values. So there is our kind of a reminder of what these opposite functions are, right? So I'm still just calling them opposite functions right now. We're thinking about them as opposites in the same way that PEMDAS has opposites involved in them, right? Okay, sweet. Okay, now I want to talk about one other way before uh, talking specifically about this logarithm question that I was asked about. Um, one more way to think about a logarithmic function, right? So, obviously, we've thought about this visually at this point where we have all of these functions. Let me just remove those ones because those aren't the logarithms anymore. We have all these various functions where um, we were looking visually at them. Um, and we know that this exponential function in green, even though it looks like it just shoots straight up and it goes off the table and it might not go all the way over this way, we know that it actually does, right? If we were to keep zooming out, then that line will actually keep going this way. But it's getting so big so quickly that this axis just really doesn't capture an appropriate scale for what we really needed to understand here. But we know that it actually does continue in this direction on to infinity, right? So where my cursor is, it continues in this direction on to infinity. And there is a line, it's just way, 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 way up there, right? If I wanted to, I could actually go over to my tools and say, well, let's just make my x axis be uh like, I don't know, let's extend it like a little ways, like maybe go out to 1,000 on it. But instead of having a comparable y-axis, let's put our y-axis up to, I don't know what, like 10 to the power of, well, looks like we're up to Some pretty big numbers here right now, right? And notice what's happening is as I continue to add zeros, I still haven't even entered where my y-axis is going to end right now. We're now, as you can tell, up to 10 to the power of 149. Up, I just ended it. But over here on my x-axis, I'm still seeing that these values are rising continuously as we continue to go right towards infinity. It's just that they're getting really, really, really massive, right? So let's reset our axes here. All right, now my axes are reset. So this is where we were. So, like we were saying, we know now that this green function continues on towards infinity. Well, the purple function is simply the reflection of the green function over the y equals x axis. So, therefore, this also does not have a horizontal asymptote. There is no horizontal line at which point this function will not cross it, right? It's gonna continue up, even though it doesn't look like it necessarily, right? So um, instead, if we're looking at asymptotes for logarithms, we're thinking about vertical asymptotes for them. So obviously, again, we said this one's a vertical asymptote of 0 right now. Here's the last part that I wanted to talk about a little bit about the another way to think about logarithms, right? So I'm just going to rewrite our logarithmic um, foundation point here, right? Which is that this is the same as log base b y equals x, right? Okay, let's think about what this statement is actually doing for us, right? It's kind of coded in this weird, obscure mathematical way, but what it's actually doing for us is it's saying if I have a function over here, like for example, 2 to the power of x equals 128 or something like that, right? And actually, an even better one than that, we know that's 7. A better one would be like, what if you had 4 to the power of x equals 128? Because it doesn't come out to be even necessarily. But if we were using the logarithmic form for this equation, essentially what we're asking when we're using logarithmic form is take the base 2 and ask 2 to the power of what number equals 128, right? So when we write this in logarithmic form, this is log base 2 128 equals x, right? And so what this question is asking you is 2 to the power of what equals 128. Now, I'm pausing just to try to let that soak in because I think that that foundational, or at least for me, that question, that foundational understanding of what the question is, for me helps me visualize things a little bit better, right? I know that 2 to the power of some number will eventually equal 128. And in fact, that one is one that we could do just, counting on our fingers. We could do 2 times 2 is 4 times 2 is 8 times 2 is 16, 32, right? And we could go all the way up to get to 128 at 7, right? Um, the problem for number 4 here is a little bit different, right? But when we ask 4 to the power of what equals 128, we could also do that by counting on our hands. We'll realize that we're over the value we needed by the time we're at an x value of only 4. So we're going to be like, oh, it must not be a whole number answer, but that's fine, right? The reason that I find this potentially useful, I guess, is because if I am trying to graph a logarithmic function, and I guess I should be thorough and put my negative axis here as well instead of just quadrant one. But in general, if I'm trying to graph a logarithmic function, like this one, let's say log base 2 128, right? Or well, in reality that's log base to x, right? Because we're graphing it for a number of different possible outcomes. And again, like we talked about earlier, the x's and y's in order to be on the same axis have to be flipped around, which sometimes can be a little bit confusing. But essentially, what we're saying is 2 to the power of what equals what, right? So as we're going up through this scenario, we're pretty much asking ourselves to start by filling in possible x values, right? Well, if I'm filling in possible x values here, and by the way, I'm just going to write what I'm graphing up here, log base 2 to the x. If I'm filling in possible x values here, then normally when I'm doing x values, I'm doing like, okay, let's graph it. What is y when x is 1? What is y when x is 2? What is y when x is 3? What is y when x is 4, right? For logarithmic functions, that kind of gets thrown out the window, right? Like it doesn't seem to make sense anymore because based on what we were just talking about, the question that you're asking is 2 to the power of what equals that value of x. Well, if I ask myself 2 to the power of what equals a value of 1, well, then that's a little easier for me to answer, right? 2 to the power of what equals 1? Well, 0, right? So I could go ahead and plot that point. But where it gets tricky is 2 to the power of what equals 2, right? So do you see how I'm just taking x values and plugging them in now? So right now, my current x value that I'm plugging in is 2, right? 2 to the power of what equals 2? Well, that one's fairly straightforward as well also, right? But what about 3? 2 to the power of what equals 3? Well, I don't know. I know there's some decimal number out there that will make 2 to the power of that number equal 3, but it's, it's a bit of an uncommon one, right? Until we get down to 4 again, right? So 2 to the power of what equals 4? Well, I know that it's 2, right? So I'm gonna go and graph that. By the way, I didn't plot my point here, but one of our values was if I plug in an x value of 2, 2 to the power of what equals 2? Well, that's 1. So I didn't mark that point earlier. 2 to the power of what equals 4? Well, that's 2, right? But my next value that's going to make sense for me is not going to be 5. It's not going to be 6. Not going to be 7, right? Do you see what I'm saying? Is that 2 to the power of what equals 7? Well, I don't know. But I do know that if I go all the way to 2 to the power of what equals 8, then there is a whole number that will do that for me, right? And it's 3. Right? So do you see how what we're doing is I got a little circle in there. I don't want that. That's not what I wanted. So what we're doing here is we're essentially doing kind of a normal graph, except because we have flipped everything over that y equals x axis, instead of going up by 1 on the x axis as I plug in different x values, it really makes more sense for me to sort of flip the script on things and to go up by the exponents of 2, right? So my next value that's going to make any sense at all is going to be all the way over at 16. And then the next value after that is going to be at 32, right? Um, Whereas we're going up by 1 on the y-axis each time, right? Because the value that I would need for 16 is the next one up, 32, next one up, 2 to the power of 5 is 32, right? So this, I think, is simply a different way to think about um, graphing a logarithmic function. I didn't even come close to the points that I had plotted there, but but we're sticking with it, right? So this is perhaps a different way to think about graphing a logarithmic function as saying, well, this is asking me 2 to the power of what equals my next value of x, right? I think that logarithm understanding can be useful sometimes when you're getting stuck on some of these weird sounding problems. Okay, now I gotta let's see, I gotta figure out what the actual function that I was being asked about earlier was. Um, be back. All right, here we go. Is the question, or one of the questions that I was being asked about. And again, like I've gone through this giant, I mean, this has been a long explanation of logarithms, right? Like from the foundations. But the reason that I'm bringing it up with such depth is because if I am graphing a logarithm, then I would probably do this right first to say, well, and you can see that we already have parent function word in this already, is this function is more complex because it's 5 times this parent function in the middle here. And then we also subtract a 5 afterwards, right? So, one thing that I would say would be useful here is to go through the same logic that we were using previously. 3 to the power of what equals. And notice that in this case, we have this negative x value here, right? But again, my x values, I think, are easier to be going ahead and putting in the multiples, not the multiples, the exponents of 3 rather than trying to go up by one at a time, right? So for me, I'm thinking, all right, well, let's start at 3, let's do 9. Let's continue from there, doing a couple more. Let's do 0 also. But the important thing to note is there's a negative out front of this, right? So the question is, what does that negative do to this? Well, it's going to take our normal logarithm function, which would be over on this side, and it's going to reverse it. It's going to go the opposite direction. Um, so instead of starting there, it's going to be whatever our value was times a negative, right? So, for example, 3 to the power of what equals 3 times the negative there? Well, it's going to be 3 to the power of 1 equals 3, except the value is going to end up being the negative 1 there instead of the positive 1, right? And if you follow this pattern up, I'm going to kind of speed things up here. If you follow this pattern up, because I do have uh, some live question sessions coming up in just a moment here. So I'm speeding it up a little bit. If you follow this up, then our logarithm will look like that, right? Again, the asymptote here, the vertical asymptote, is still 1 because it just got reflected across the y-axis in this case. But the question is, what does this times 5 and then minus 5 do to the values that we're getting from this, right? Well, the question previously was 3 to the power of what equals 3. The answer was 1. We multiplied by the negative out front, so we put the negative 1 there, right? However, um, what we oops, I put that in the wrong spot. I was looking at 3 and then I just did it for the 0 spot instead. So that was just me overlooking stuff. Um, but again, the question is what happens when you then take that value? So in this case, we got our value of -1 there. What happens when you take that value and then you multiply it by 5 and then you subtract 5 from it? Well, what is not going to happen is that this function is not going to be moved to the left or the right, right? So that means the asymptote is going to stay the same. What will happen is that this function might get stretched vertically, right? Or, and by the way, this is kind of being posed as a question for you right now, kind of a summation of everything we've done. Can you figure this out? Or would it get stretched vertically, or would it just be pushed upwards? And then, second thing, what's this -5 going to do? Well, presumably, it's going to take this whole function after the stretching and just move it down 5 on our y axis. So I think that hopefully that's a lot of background onto logarithms that could tell you a little bit more about how you could visualize graphing them without perhaps going ahead and plugging it into Desmos. Now, again, we could plug this into Desmos as well. Um, I'll leave that to you all to do because I'm going to run off to my office hours now. Hopefully, this was helpful. Thanks and see you next time.